The following is a project made for the Intro to Feedback Systems class at the Colorado School of Mines by the students Anya Wiens, Elior Bilow, and Ambryn Fortier. All team members work together in order to compile information in this presentation. Papa Jim's pizza is fictional. Please don't call the number at the end of the video. Thank you to our professor, Salman Mohagedi, and to the internet for teaching us what we needed to make the delightful video that you are about to watch. Do you like pizza? Do you want pizza now, delivered to your door, free of charge? Papa Jim's Pizza is utilizing modern drone technology in order to get pizza from their oven to your door. Imagine that beautiful, warm, filling pizza arriving at your doorstep. But you ask, why didn't I know about this earlier? Well, let me tell you a little secret. Papa Jim started his futuristic deliveries in the fall, but it was a disaster. Luckily, Papa Jim was able to keep it on the DL and hired our team to fix this problem so that now you can receive your delicious pizza. In this video, we'll show you how we were able to fix Papa Jim's drone delivery service so that you can get your pizza as fresh as ever. As with all projects a design team fixes, well, attempts to fix anyways, it's best to start at the root of the problem. We visited Papa Jim and his unsatisfied customers, and they reported that they were receiving their pizzas ruined during transport. Pizza slices arrived overlapping one another, and pizzas were stuck to the tops of boxes. We figured that the problem could be solved by implementing a better controller on the drone, a PID controller in particular. This saves a pizza from having traumatic injuries during flight before arriving at the door of the hungry college student ordering the pizza. The controller can control the transient response of the drone, as well as its stability and steady state response, ensuring that the pizza doesn't accelerate too much so that the box gets shuffled around, and making sure that the drone doesn't crash into trees, buildings, or power lines during flight. Another reason why we added a controller was so that it could reject disturbances like wind. The first step in making a controller was finding the transfer function of our plant, which is the drone in this case. We started by looking at the forces acting on the drone, lift from the propellers, gravity, and air resistance. Combining these forces into an impedance circuit allowed us to find the transfer function G of S, which was the combined impedance of the damping force of air resistance and the drone's inertia. The transfer function was then used in this open loop system to determine the response of the system, which in this case is the height of the drone, H of S. We assumed gravity was constant and lift was a unit step. Testing the system resulted in adverse results. The drone kept on going up, meaning that the system was unstable. We can confirm this with a plot of the function's pole locations. There are two poles located at the origin, making this system unstable. Since the open loop system was unstable, we immediately knew that the system has to be a closed loop in order to function properly. We also opted to add a controller in this step since, you had to do it eventually, and now is as good a time as ever. With our controller now in place, it was time to decide how we wanted the system to respond when we told it to take off with the fresh pizza. We need the drone to move slowly so that the pizza doesn't go flying around, so we need to have the following transient response criteria. The takeoff can't be too extreme with too much acceleration, so we chose to have a rise time longer than at least 12.5 seconds. With that same thought process, we don't want the drone to oscillate very much once it gets near its final height, to prevent the pizza from getting jostled around, meaning that the overshoot also needed to be low. We decided on setting the overshoot maximum as 10%. The combination of a proportional and a derivative controller can control these first two criteria. The proportional controller determines the distance between the drone's current height and the desired height, also called the air, and adjusts the propeller force accordingly. As the air gets smaller, the force from the propeller decreases. This can stabilize the system. The higher the KP value, the faster the drone will rise, which decreases the rise time. However, going too quickly can cause the drone to go past the desired height, resulting in greater overshoot. That's why we added a derivative controller. The derivative controller predicts the future path of the drone to smooth out the drone's response and minimize the overshoot when combined with a proportional controller. But there's one more controller that we need in order to clear the buildings, trees, and power lines: the integral controller. Using technical terms, the integral controller affects the drone's steady state response, which basically means that it will make the drone end up at exactly the height that it needs to be. It does this by looking at the past behavior of the drone in order to decide if the drone is actually at the height that it should be at, or if it's not. If it isn't, it will tell the drone to adjust its lift force accordingly. For Papa Jim, we think that a final height of 75 meters will be suitable in order to clear all the buildings, trees, and power lines. Time to get back to testing. Using the Simulink software, we were able to test different KP, KI, and KD values until we found some that met all of our criteria. In the end, we found that a drone with a takeoff weight of 5 kilograms and a drag coefficient of 1.2, the best PID coefficients, KI, KP, and KD values needed to be 0.1, 0.8, and 0.8 respectively. These values are specific for our drone, so if you try to do this with a different drone, your PID coefficients will be different. To find the transfer function for our system, we use superposition. Performing a root-through stability check shows us that the drone flight is stable since all of the numbers in the first column are positive. Since the drone height is stable, we can use the final value theorem to make sure that the drone ends up at a final height of 75 meters. With the tune controller, we found the transient response of the drone while it's affected by gravity to meet our criteria with a rise time of 14.7 seconds and an overshoot of only 0.009%, which is basically nothing. Also, the drone ended up at the final desired height of 75 meters. Very nice. Finally, it was time to put the drone to the test and see if it can perform while facing off against its worst enemy, wind. We added the disturbance to the simulation for wind, and, to our luck, the drone still worked. Even though the wind slightly affected the drone's height and made it go up or down a little, it was always able to correct for the disturbance and return to around 75 meters. We can verify these results mathematically by using the final value theorem on the stable drone. As you can see, the disturbance of the wind approaches zero as time goes to infinity, so the drone will stay at 75 meters. Even though the drone will return to 75 meters no matter what, when the wind exerts 7 newtons of force on the drone's overshoot was over 10%. Unacceptable. Luckily, this correlates to a 20-mile-an-hour vertical wind speed, which is quite rare, so Papa Jim's drones will be able to fly almost all the time. With the maximum wind scenario, we found that the highest force that the propellers exerted was about 120 newtons right when it takes off. Therefore, the highest acceleration is also at the start, which is about 14 meters per second squared. After it stabilized, the propellers exerted roughly 50 newtons with 10 newton fluctuations. With a stable drone and great PID coefficients, we were finally able to destroy it. Test it and see when it breaks. Using the Bode plots, we were able to calculate the gain and phase margin. The phase margin was 80 degrees at a crossover frequency of 0.5 radians per second, while the gain margin was... This can't be right. The gain margin is infinite, since the phase diagram never crosses negative 180 degrees. Looking at the Nyquist plot verifies this as well, since it never crosses the negative real axis. So, we can't break the drone by giving it too much gain. How else can we break the drone? How about by making it respond too slowly? Using the phase margin and the crossover frequency, we use this equation to calculate the maximum time delay of 2.79 seconds. To verify this, we added a time delay to our Simulink model and proved that with such a delay, the system will become unstable. Right on! Oh no! With the brand new PID controllers on Papa Jim's drones, he can finally start his delivery service again. So what are you waiting for? Call 314-159-2653 in order to get your pizza today. You like pizza, right?